The solution to this lab can be divided into 3 separate phases, each one consisting of its own concept of physics. The first phase deals with conservation of energy, as the potential energy of mass 1 is converted to kinetic energy as it follows its trajectory and eventually collides with mass 2. This brings us to the second phase, which is the conservation of momentum. Mass 1 collides with its initial velocity to the stationary mass 2. In the end, it's a perfectly inelastic collision momentarily, so that the combined masses have the same velocity. After the conservation of momentum, you can use a combination of forces or kinematics to figure out the displacement and eventually the force of friction that causes mass 2's velocity to eventually become 0. We will now show all the calculations used to derive mu in this lab. At the top we have all of the listed values that we recorded as we conducted the lab, and similarly to the diagrams, we've divided the calculations into 3 phases, each one dealing with a different physics concept, the first being conservation of energy. As shown, we use the conservation of energy equation, consisting of both the potential energy and kinetic energy pieces. After getting rid of mass and performing the calculations as shown, we found that the final velocity was 3.1148 meters a second. That was the velocity of the ball as it came and struck the cart. Phase 2 of the calculations uses the conservation of momentum equations. We noted that it's a perfectly inelastic collision for our purposes, and that the initial velocity was 3.1148 meters a second, which we found in phase 1. After changing and moving around the variables, we were able to find that the final velocity of the system after the conservation of momentum occurs is 2.0116 meters a second. For our use, this will be the velocity of the block as it begins to slide across the paper. The final phase of the calculations uses a combination of forces and work. We noted that work is equal to force times displacement times the cosine of the angle between the two, and that is also equal to the change in kinetic energy, which delta K could be 1/2 mv squared initial minus final, but in this case we would use just 1/2 mv squared. After plugging in this equation and realizing that the force we're looking for is the force of friction, and that there is no angle between the two, we're able to discover that the force of friction can be 0.2418064581. And after plugging this into the mu of kinetic energy equals force of friction over the normal force, we finally discovered that mu for kinetic energy was 0.36.